Good morning, everybody. My name is Ibrahim, working for ETAS Bosch for more than 10 years already. And in its last 6 years, I was working in different roles in the area of updates over the air for vehicles. And I'm happy to show you our ideas and solutions about the next generation OTA updates. But first, I would like Bala to introduce himself quickly, and then we will start with the presentation.
Hello, everyone. So my name is Bala. I'm also working in Bosch for the past 14 years, and I'm working now in the onboarding team of ETAS, responsible for onboarding customers onto Mobility Cloud, and also working alongside with Ibrahim for OTA NG.
Thank you, Bala. So then let me start directly with the overview of the today's webinar. So I will give you a short overview about ETAS, that you get a feeling of where we are coming from, and the software-defined vehicles, trends and challenges which will be faced in the future, and which type of solutions are needed there. And then a deep dive on OTA updates next generation, starting with basic principles of OTA updates, then the explanation to the new paradigms, and some aspects of onboard and offboard architectures on that aspect. And then I will summarize with a short portfolio overview and give you also an overview of the open source initiatives we are part of and partnerships, and close with that overview. So ETAS was founded as a subsidiary of Bosch in 1994. And started with measurement and software development tools for embedded ECUs. We are now located in 12 countries, have a brand associated with us, eScript, which is known for their security expertise, in particular for automotive domains. And today we are more than 1,500 associates, and next year this number will increase significantly because we are consolidating software development departments from Bosch into ETAS in order to get these horizontal layer offerings consolidated at one place to also optimize our offerings and our developments. If you look at our portfolio, we have 6 solution fields, starting with development for software of embedded and other automotive domain ECUs and applications. Usually these are model-based software engineering tools and also simulation tools like software in the loop systems. We have this vehicle operating system solution field, which provides classic AUTOSAR, OS, adaptive AUTOSAR stacks, and also stacks for the autonomous driving systems. Vehicle cloud services was already mentioned by Bala. This is our mobility cloud, which provides various services around OTA updates, data management, or remote diagnostics. The cybersecurity section solution field is, as I mentioned, the eScript colleagues, which provide you consulting services as well as products around security in the vehicle and also in the connectivity of the vehicles. And data acquisition and processing includes tools like Inca. You might have heard that from ETAS, which can be used to access ECU data in the pre-SOP phase and analyze them and process them with hardware support like ETKs and other access and measurement tools. The end-to-end solution field is the solution field where I'm located in, where we bring all these single products of the solution fields together and provide end-to-end solutions integrated. And one of them is OTA updates, and we will look at that in more details. But let's first look at the trends of software-defined vehicles. You might have heard that term more and more in the last 2 years. So there was a mindset change, I would say, in the last 2 years, that it was more and more clear that the number and amount of software in the vehicles will increase significantly in the future, and that software will be the dominant or value generation also for vehicles. So that means the portion of software and the value of software will increase for vehicles. And if you look at the e-architectures, the trend of increasing number of ECUs, embedded ECUs, will be reverted. So that means a consolidation will happen and we will move to EE architectures where you have one or more high-performance computers which consolidate these embedded features and functions which were located in different ECUs into single boxes. And this will simplify the EE architecture itself, but also give the possibility to reuse code which was developed for embedded ECUs now on high-performance computers. And this has many aspects and results, but one of the most important one here is the decoupling of hardware and software. That means, in contrast to the past where you have developed ECU software for one certain ECU and for one certain model, and you were happy when this software was running and were hoping that this will run for the next 20 years and no updates needed at all, and the developers could focus on new projects and new development tools and also new developing vehicles. That will change in future. So if you have more and more software, you need to decouple that from the hardware, and you want to reuse that software over different models and brands. And in order to get that, you need to also move from this classic V2V model to a DevOps concept for also embedded and automotive software. That means you develop your code, you release it, you deploy it, and then you monitor and improve that code and deliver it again, either to the existing models or to new models in the future. So that means the OEMs and also suppliers need to change the way of developing software for autos and vehicles in future, and this starts with organizational aspects, but also this needs some software solutions to support that transition. And if you look at these main requirements for software-defined vehicles, we think that this is the ability of organizations to deliver software in a fast, efficient, and safe way to the vehicles. So in the past, you know, there were some model cycles starting from 7 years. It was optimized into 3 years, but still, for classic vehicles, if you develop software, new software features, it takes months to years to get that designed, developed, tested, and released, and that needs to be much, much, much faster. You might know from some OEMs, new coming OEMs, that they are able to deliver full software releases in weekly mode or monthly mode, and this is something which we think that all the OEMs in future need to be able to do this in the same way if they want to be players in the software-defined world, software-defined vehicle world. And if you look at the end-to-end solutions, the 3 main solutions we think which are relevant is to have a vehicle application development framework which supports you to have a fast development process. And we assume that you can develop applications so containerized applications in the QM domain compared to the embedded ECUs 10 times faster. You need to deploy them at scale to many vehicles in the field, and again and again. So that means you have a increasing number of updatable vehicles, but you have to update also often. And in order to be able to do that, you need a respective solution which supports you doing that. And once the software is in the field, you want to learn from the software and the insights from the field. So you need to be able to collect data from the vehicles, provide it back to the cloud for analysis and to the developers to optimize their application. So that means we get to a loop, to this DevOps loop. And I will focus today on this over-the-air updates aspect, which I will show you in the next slides in detail what we believe what is needed in future. And this is the basic principles of OTA updates we have already working today. So we as ITAS Bosch, we have solutions in production with OEMs in different regions working like according to that concept, but there are also other solutions in the market working in the same way. So usually you have your ECU firmware or application executables and some update control artifacts that can be some diagnostic sequences which describe how these respective binary have to be flashed on the respective ECU. They together are used to be packaged together, one or multiple binaries if you have dependent ECUs, and respective control artifacts are packaged together and uploaded to a backend, which can be a cloud-based or non-cloud-based backend. And from this backend, you can then select or define which packages are distributed to which vehicles. Usually the term campaign management is used for that. So you can assign it to single vehicles or to multiple vehicles based on some criteria. And then the vehicles get notified that there are update packages. They download those packages, extract the content, and install the packages on the respective hardware. And provide an update reporting if that was successful or not. And they will regularly also report their current inventory or the current state of software which is installed on that vehicle. So this is a basic principle. And of course, there are two important cross-cutting aspects which have to be also realized. One of them is security in all of these phases, and also in the interfaces of these phases, there are respective security requirements which have to be fulfilled. I will not go into the details of these aspects today, but just highlighting this with these dashed lines that we have solutions in place for these, which are quite important aspects of end-to-end connected vehicles. And the second one, if you go into the vehicle, that's a safety concept that needs to ensure that you perform updates on embedded ECUs only if the ECUs are in a safe state or the vehicle is in a safe state. And usually that's in the parking mode and maybe a confirmation from the driver that the vehicle is in a safe state. So this is how the OTA updates work today already. And let's look at the reason why we think there's a paradigm change needed. So if you look at the vehicles today, about 100 ECUs. It's common in some types of cars, but the majority of these ECUs are never updated. As I mentioned, these have been developed, and the hope is never update these ECUs again. They will work for 20 years. If there are some quality issues, safety or security related issues identified, then of course you need to provide an update to those ECUs, and either you do it in the workshop, so you recall the vehicle to the workshop, or you do it over the air. And if you do it over the air, then you have dedicated update campaigns. That means you need to know all the variants in the field. You need to create dedicated update packages for those variants which fit their current state. And then you need to distribute those packages to those vehicles. And usually these packages are created manually. So at many OEMs currently, it's a manual process to identify which software goes to which vehicles and create the respective packages. So there are some numbers. We got to learn that around 30 people at one OEM are working full-time and managing these campaigns for all the variants in the field. And I think you agree that this is not how it should be done in the future, because we will get vehicle applications, containerized applications. That's a term coming from the containerized cloud world. And this combined with multiple domains like classic ECUs, adaptive AUTOSAR, autonomous driving systems, infotainment systems, will enable OEMs to deliver new features over time to those vehicles in order to keep the vehicle lifetime value high and be able to compete with the competitors like newcomers. We know that Tesla, for example, is able to deliver software often to their vehicles. So that means we will not only solve bugs and have updates which are resulting from bugs, but we will continuously deliver new features and improved features to our software-defined vehicles in the future. This increased demand for OTA updates will also lead to an increased data transfer. So that means this is a costly data transfer across mobile networks, and this will be a challenge we have to cope with, and we will talk about that in a few minutes in detail. And the increasing individualization, these vehicle applications, which can be then which can lead to users subscribing to some features or canceling subscriptions or purchasing new features, or you have other aspects why the software of these vehicles can be then individualized. That means the variant problem we have, a challenge we have discussed on the left side, will even be bigger if you go towards software-defined vehicles, because you will be having higher number of software and hardware combinations in the field. And one topic which we think which will be relevant in the future will be the context-aware software-defined vehicles. That means the software-defined vehicles need to adapt their software configurations and installations according to their usage context, and this usage context is determined by different parameters. And one of them is, for example, the usage scenario. Is it a rental car? Then you might need to install some applications which are delivered by the renting company. Or it's a privately owned car and the user has purchased its own applications. Or it's a leasing or company fleet car, then you have additional software which you need to install on this vehicles. In addition to this usage scenario, you have the location. You might need to comply to some regulations in certain countries, and if this vehicle is running in that vehicle, then you have other software running than in other regions. You might also, for example, if you have rental cars and you want to limit the radius which this car can be used in, you can configure that via software. The time frame, might heard about BMW, which is now promoting a seat heating application for 17 euros per month. So that means in the winter you can buy this feature, in the summer you can cancel that feature, or you can buy some additional horsepower in the weekend and additional user settings. All of these artifacts and parameters can have an impact on the software running on the vehicle, so that means the context implies the desired state. So desired state is the term which we use to describe the state of software configurations running on a vehicle which we want to have running on that vehicle. And this is usually depending in the future based on context, the usage context of the vehicles. So how does it look now in detail if you look at these two paradigms? Classic approach, you have dedicated update campaigns with different composite packages. A composite package means you have one package, one vehicle package, and it can contain artifacts of different binaries for the ECUs, like in this example, perfectly keyless or crash detection. And this composite package is then sent to the affected vehicles which have a certain variant of software state. And these vehicles then will download the full package and install the containing applications. What can happen is that today there's often the issue that the OEMs either don't know what is the current state of the vehicles, because there might have been some software updates in the workshops, or even some vehicles were not online for a long time and then they did not get any updates. And this leads to variant and dependency management effort in the backend, which is quite high already today. And we read that in the news, and this will be increasing in the future. And we think that this is not the solution how it should work. No prepackaged dedicated composite packages to the vehicles, but let's move to the desired state approach. And this desired state approach is an approach which is already working in the cloud world. So this comes from the infrastructure as code term, which is used there. Also the system state is described in a declarative way. That means you provide the desired state to the system, and the system performs the actions needed to get to that desired state. And in a vehicle case, that will mean we don't have prepackaged packages, but only the single artifacts in our software repository. And our cloud is smart enough to calculate a desired state which fits to my vehicle. And here you usually don't need to know all the details of the current state, but you just, based on the context, define what is the desired state, and then the vehicle individually will decide what steps to perform in order to get to that desired state. So it compares the desired state and the current state, and for the mismatching parts, it decides, do I have to delete something, do I have to download and install or update something. So that means we are moving intelligence towards to the vehicle, indicated by that icon compared to the left side, and the vehicle takes some responsibilities of identifying which steps to be performed in order to get to the desired state compared to the classic world. let me show you some architectural aspects on how this desired state can be applied in the vehicle and how that can be compiled and generated in the backend. So let's look at the onboard side. This is an example deployment EE architecture you might find in future software-defined vehicles. So usually you have a compute domain where you have a connectivity device which is able to connect to the cloud to get the desired states and software packages downloaded. So that means we have a context pipeline in the mobility cloud which is generating the desired state. I will show you details of that context pipeline later. We have an auto update service which then distributes those desired states and software packages to the vehicles, and connected vehicles layer which is handling the communication protocols between the cloud and the OTA client of the vehicle side. This OTA client then downloads this desired state, and Bala will show you later an example how such a desired state can look like for applications. We'll download this desired state and hand it over to a so-called vehicle update manager, which is responsible for the vehicle-wide orchestration of the updates. And usually there are different types of updates which can be applied to a vehicle, and the first one, sorry, I clicked the wrong button. So the first one is the self-update. So usually each of these Linux-based devices, they bring their own self-updater, which we call a local updater, and this self-updater needs to be called by a so-called update agent, which is able to translate the desired state description to concrete action or API calls for the local updater. So that means the vehicle update manager here and the self-update agent, they interact in order to share the desired states partially and then call the local self-updater. The second domain we have in our vehicle is the container world, containerized application world. So you have a container runtime like Containerd, and you have applications running on this container runtime, and now you have a container update agent which interacts with the vehicle update manager using the same APIs like the self-update agent. The vehicle update manager hands over the parts of the desired state to this update agent, and this one translates this desired state to the respective update commands for the domain update manager, which is usually a container manager in the containerized world. The next domain is the safety domain, which consists of embedded ECUs, for example, classic Autosar ECUs, which support UDS-based updates, or we have adaptive Autosar ECUs, which also bring already some standardized components like the UCMM, so Update Configuration Management Master, and the UCM, the Update Configuration Master, which are already standardized applications in the Autosar world, and we are reusing that. So that means we are not reinventing the wheel there, but we reuse already standardized solutions where possible in order to perform the update of the adaptive and classic Autosar ECUs. In the next slide, I will go a bit more into the detail of these embedded ECUs and their capabilities, which would then affect the user experience in this future of vehicle drivers. And this flashing adapter is the update agent, which then is able to flash one or multiple embedded ECUs. So that means you have another update agent for the UCMM, which translates between the vehicle update manager and the UCMM in order to get the respective software delivered to the target ECUs. And another example domain here could be the Android Automotive operating system, which we are seeing more and more in the future vehicles. And that means if you have Android apps or you have core image update of the Android system, then you would use this update agent for Android and then implement the same APIs. So that means in this architecture, two main messages. You can apply this desired state to various domains, and you can do that by implementing unified update APIs, which then can be delivered by update agents. Either we provide the right ones, or third parties can provide. So either the OEMs can provide their own update agents for their domains, or suppliers which bring their own types of ECUs with some specific and proprietary update mechanisms. But this can be integrated like a plug and play approach into this vehicle update manager if the respective APIs are implemented. One look at the target ECUs. So this is really the classic embedded ECUs, which we know from the past. They have usually this base capability. So they have a bootloader, and you can flash the image across this bootloader to the memory using an external tester, and this external tester will be the photo master in the vehicle. So the disadvantage of the solution is that the time for updating this ECU takes long, and the vehicle is not usable at that time frame. So that means one example, if you have 5 ECUs, each 8 megabyte big, and you update them one after each other, then you would need 60 minutes to update 5 ECUs using this base system. And if something fails, and these are dependent ECUs, and you have to roll back all of them, you need another 60 minutes for a rollback. If you go to the base plus approach, then you can add additional memory, internal memory to this ECU, which is not executable, but you can transfer this update to this second memory part, and then you can internally swap that to the executable area, which then doesn't speed up the update time, but the rollback internally is much faster, and then you can at least save some time there. But what we propose and we recommend is to go to these enhanced or premium versions, where you can reduce the update and rollback time significantly, either 2 minutes in this enhanced variant or even 1 second in the premium variant. That means you have more memory, and your application, so you don't need to go to the bootloader mode. Your application is able to receive these UDS commands and write the software into the extended memory in the background while the vehicle is driving. So that means the driver comfort is increasing extremely if you go to enhanced and premium ECUs, and the vehicle downtime is reduced accordingly. The disadvantage of the solutions is, of course, the cost. So that means if you have additional memory and executable memory, then you have to pay more for those chips, and that's one big issue today, why these ECUs are not deployed in a large scale today. We have at Bosch already a software solution, which can be applied to these ECUs with additional memory, and we have it productive in Bosch ECUs, but this software stack can also be applied to third-party ECUs with classic AUTOSAR stacks. Let's have a look at the offboard side. In the offboard side, we have a mobility cloud, as Bala mentioned, which comes with several layers. You have a core services layer, which allows you to deploy new software services in the managed runtime. Your software developers can use this portal to deliver new software services to the mobility cloud. There's a data integration layer, which can integrate data either directly from vehicles or from third-party cloud solutions, or also send data to the third-party cloud solutions. And then we have our OTA services, and over-the-air update is this service which is needed for our end-to-end OTA update solution. In addition, we have vehicle data services, we have function calls which can be used to execute remote diagnostics functions, or even, let's say, open the trunk in the vehicle over the air. And the connected vehicles was responsible for the connectivity. So this over-the-air update service is used in our approach to distribute the desired state and manage the progress of the desired state, so to monitor the desired state progress, but it's not the one which generates the desired state. Therefore, we have the idea of a so-called context pipeline. Context pipeline is aware of the context of the vehicles in the field by consuming data from different sources, like a fleet management system, from where I can get the location of my vehicle, I can get the current state, if needed, the current software state, but I can also get from other systems, like if there are any subscriptions for that vehicle, if there are any specific apps to be installed because they have different usage types. And this context pipeline can also consume software hardware dependency descriptions, which are available in some databases at OEMs usually. And based on these inputs about vehicles and generic hardware software dependencies and the existing software, so in my software registry, when I have a new software updated to my software registry, I would get additional information to which I can consume. That new software is available, and I can have a fleet manager which can explicitly assign a new software to a group of vehicles. For example, if I have a security issue and I know all my Mercedes C-Class vehicles are affected by that, then I can define a vehicle group. All Mercedes C-Class in Germany should get this new software package. I can do such kind of mapping here, and all these different types of events are then consumed by the context pipeline to calculate a desired state for each of these vehicles. And in the second step, before the desired state is sent to the vehicles, this desired state needs to be validated as well. So that means this context pipeline has an integration in various data sources, as well as various tooling like software in the loop systems, which are able then to take dependent ECU software releases and validate them together before this is sent to the vehicles. This is a quite big task shown only in one block. We have started working on this conceptioning and developing first prototypes of this context pipeline, but we are not at the end of the journey here. So that's one of the challenges we are working on, and we are happy if you have interest in that topic and would like to get in touch with us. So let us know that one. This part I have shown already earlier. So when the desired state has been released, it is distributed via the OTA update service from the mobility cloud to the vehicles, and then the vehicles download only those artifacts which are needed to get to their desired state. Let me summarize quickly what we have introduced today. We have argued that a declarative OTA update solution can be the answer for the challenges of OTA updates for software-defined vehicles. And we have shown that this is using new software paradigms which are coming partially from the cloud world, like a system as code approach or the desired state approach, and that this can be applied to all in-vehicle domains via unified APIs. The benefits I have here is that I can manage individual vehicle software configurations at scale using that declarative approach. I reduce a manual configuration effort in the backend, and I transfer some responsibility to the vehicles, and that simplifies my management effort in the backend. And by enabling and allowing vehicles to get software updates over time, over the vehicle lifetime, I will increase the lifetime value of my vehicles, and I will, as an OEM, be able to compete with my competitors in the market. So I have 3 minutes left. I see I will quickly go through the last slides here. This is an overview about our portfolio, which we are providing as shown in the previous slides. I will not go into the details here. Just some highlights about the features of this portfolio. Of course, updates need to be secure. Updates need to be safe for vehicles. They have to support all the in-vehicle domains, and they have to be compliant to regulations, and cloud solutions to be able in multi-regions in the world. And all these features we do provide as ETAS and Bosch together. We support legacy ECUs, we support new types of ECUs. So if you have interest in this, I'm happy to answer details. But let me go to the last slide and highlight also our initiatives in the software-defined vehicle world in Eclipse working groups, SDV, for example. We are one of the founders of this working group. Together with Microsoft, we have started that activity already 2 years ago. And now you see that group has grown already. We have CARIAD and Toyota from OEM side. We have Bosch, ZF, and Continental from the ECU supplier side. But we have also ARM, NXP from the silicon vendor side, and Microsoft from the tech world. SUSE, Red Hat, open source contributors from the Linux world. So you see really very competent group here trying to get the standards for software-defined vehicles to the market, and also doing that not only based on specifications but also based on code. And we are contributing to that group. We have already 2 projects there with source code. This is Velocitas for the vehicle application development aspects, and we have LEDA, which is putting together everything you need to have this edge stack, this containerized application edge stack running. And we are delivering there the update components, update agents for self-update and for container updates. There are also other initiatives in the open source world, like Sophie and Covesa. Covesa, for example, is focusing on the vehicle signal specifications in a unified way, so that application developers don't need to take care about all the details of different hardware providers, but they can access vehicle data through those standardized APIs. And we are collaborating together to get these software-defined vehicles in the industry on the same standard way, so that everybody can focus on differentiating aspects, but the non-differentiating aspects are delivered as open source and can be reused by all the players. So that's my invitation also here to you to look at these open source initiatives, and let's shape the future of SDVs together. This is my presentation. I'm done now. My time is also over. I would like to hand over to Bala for taking the demo part, and then I'm happy to answer your questions.
Thank you, Ibrahim. So let me set the stage for the demo. So what do we see in this demo is that we have 2 devices. So device 1 and device 2, they both have the Eclipse LEDA, like Ibrahim said, as the edge environment, having a Kubernetes environment running in it. And on these 2 devices, we have prepared a set of initial state for the devices. So we have certain apps in different versions, and we have also certain apps here in the different versions. Say, for example, Seat Service is in version 17 here. Data Broker is on version 18. Whereas if you see on the device 2, we have Seat Service exactly the other way around. We have the 18th version, whereas the Data Broker, we have the version 17 here. And we have one more app called Seat Adjuster app, which we don't want to have it on the device. So now, how do we bring both these devices having different initial states to consistent desired state? So that we do with the help of the desired state specification. So in the desired state specification, we say that we want Seat Service app, Data Broker, and a new app called FeederCAN app, all in version 18. And once this desired state is handed over to the devices, the device uses its own intelligence to compare what it has to do in order to achieve that particular desired state. Say, for example, device 1 will look the version 17, compare it with 18, and then it will decide, okay, I have to download the new Seat Service application. Whereas I don't have to do anything on the Data Broker side, it will leave it untouched, and it will also download the FeederCAN app, which is required here in order to reach this desired state. So because of this intelligence on the device side, like Ibrahim told, the device will use minimal bandwidth to download only their absolutely required packages and leave the rest out. If you see the device 2, it will keep the Seat Service untouched. It will download the new latest version of the Data Broker, version 18. It will then also download the FeederCAN app, and it will uninstall the Seat Adjuster app, which we don't want to have. So if you look at, I can show you the devices right away, which I have prepared. So if you see here, so these are the 2 apps, the Seat Service app and the Vehicle Data Broker app. In addition to other applications, what Ibrahim already told. So we have the Cloud Connector for connecting with the Mobility Cloud. We have the Mosquito Broker here, and we have the Self-Update Agent and the Update Manager. So these are standard apps. So in addition to that, we have these 2 apps. So, and the same way on the device 2, we have this unwanted app, Seat Adjuster app, which is which we want to throw it away. And we have the Vehicle Data Broker and also the Seat Service app here. So the FeederCAN app, which will come with the desired state, is not available on both. So if I have to compare the versions right now on the devices, so you can see the FeederCAN app on both sides is missing, which will come with the desired state. And we have seed service in version 18. Here we have it 17 and 18, and the other way around for data broker. We have 18 here and we have 17 here. And now I will use the mobility cloud to apply the desired state on both these devices. So how do I do that? So I have predefined all the packages that are required. Basically, the packages contains this declarative software stack YAML files, which are pre-uploaded onto the mobility cloud. So they are nothing but these YAML files here. So if I have to compare 511, that's the current state of device 1 with the target desired state. So you can see here. You can see that's only the versions are changed here. The seed service will be updated to version 18, and a new app FeederCAN will be introduced onto the device 1, whereas the data broker will remain untouched. So there is no changes there. And the same thing can be done for the second device stack. So if I have to compare the current state of device 2 with the desired state, so the data broker will be updated, seed service will remain untouched, and the FeederCAN app will be introduced, and the unwanted seed adjuster app will be removed. So I have uploaded these YAML files already here, and I have also defined the distribution packages. So distribution packages tells how we can send those update packages to the devices. So for example, whether I want to have the desired state packages signed or not, whether it has to be signed and encrypted, for example, then you choose encryption. So depending upon the requirement on the OEM side, you can have different options here for sending the package down the wire. So I have also prepared the distribution packages beforehand to save time. So we have 3 packages. These were applied on the devices initially to bring them to the current state. And now we'll apply the target 5.2 onto the devices. So how do I do that? I don't go to the individual devices to do the assignments. Rather, we can start a campaign to address more than one vehicle or a group of vehicles, depending upon filter criteria. Let me go and do that. Assign desired state 5.2 to all demo vehicles. And I'm not going to give any start date, end date here, because I want the campaign to start immediately. I'm going to trigger it manually. And you can also here specify how many vehicles you want to have it updated in parallel. And you have other additional opportunities like having a dynamic campaign, meaning that after the campaign has started, if a vehicle matches this filter criteria, whether it can be added or not can be specified here. And whether you need any separate approval from the OEM backend, for example, can also be specified here. Or if you need any manager approval, fleet operator, for example, if you need those approvals, then you can also include that in the campaign. I'm not going to do that for the demo right now. Let me click save. And now that it's a pretty empty campaign, let me go and specify the vehicles. And have 2 vehicles, like I said, containing these 2 devices. I have them selected now, and let me choose the content 5.2, which is the desired state which we want to apply on the devices. Now the campaign is ready. I can schedule it, and I will schedule it now and switch immediately to the device side so that we can see the update live. So the scheduling is done, and in a few seconds you should then start seeing the changes here on the device side once the desired state is received by the device, and it checks the current state and then has to do the update by itself. So here you see the seed service gets updated, a few FeederCAN app, new app is getting installed, and on this side you see the vehicle data broker is getting updated. And one advantage is that only when the new app is successfully running, the old app will be terminated. Till then, the old app will continue running. So in case if there are some inconsistencies in the newly delivered application, for example. So it's being terminated, but on the whole, everything was evaluated and the update was considered to be a success, which we can also now see on the campaign here. So we have the update success reported back to the mobility cloud. So with that, now we have brought both these devices having different context, initial context, or initial state. With the help of desired state, we brought them to a consistent state containing these three apps, and the other unwanted apps were removed. And we can also now compare it here with the versions. I can print it again. So here you can see the seed service was updated from 17 to 18. Data broker was untouched, and a new FeederCAN app version 18 was introduced. The same thing can also be observed on the device 2. So yes, seed service was untouched, data broker got updated, and FeederCAN app was introduced. So with that, now we are now able to do the same thing what we have till now done on the cloud side. We can now do it on the device side using the desired state update mechanism. Thank you. So I'll hand it over back to Ibrahim.
Thank you, Bala. So we have seen really that each vehicle performs different actions in order to get to the same desired state. And we are improving our mobility cloud already, that we can also visualize the desired states of each of these vehicles and show the progress and the history of this desired current states, so that we can keep track of what has been installed when. Thank you very much.